This is section 8.4, day 2. In example 6, we have an infinite discontinuity at an interior point. Notice the function is 1 over x minus 1. 1 makes the denominator 0, and 1 is in the interval from 0 to 3. So we're going to have to split this integral up into two limits. The first limit is the limit as c approaches 1 from the left of the integral from 0 to c of dx over x minus 1 to the 2/3. Now we're going to write that as the limit c approaches 1 from the left of the integral from 0 to c of x minus 1 to the negative 2/3. Then we can use the power rule to take the antiderivative. Limit as c approaches 1 from the left of 3 times x minus 1 to the 1/3. There's the antiderivative. We're evaluating this from 0 to c. So let's plug c in. C approaches 1 from the left. 3 times c minus 1 to the 1/3. And we'll plug 0 in. We get minus 3 times 0 minus 1 to the 1/3. That's equal to the limit as c approaches 1 from the left of 3 times c minus 1 to the 1/3. 0 minus 1 is negative 1. Negative 1 to the 1/3 is a negative 1. And negative 1 times a negative 3 is going to be plus 3. Now we want to find the limit as c approaches 1 from the left. So we have 3 times 1 minus 1 to the 1/3 plus 3. And that's going to equal 3 because the left-hand side of the plus, that's going to end up being 0. Well, now we've approached 1 from the left. Now we want to approach 1 from the right. So we have the limit as c approaches 1 from the right of 1 to 3. And notice that in the original problem, it was from 0 to 3. So we have dx over x minus 1 to the 2/3. And we don't have to repeat the process to find the antiderivative. I can skip to this part right here. So we're going to do that. Equals limit as c approaches 1 from the right of 3 times x minus 1 to the 1/3. This time c is going to be on the bottom. Whoops, I shouldn't have wrote the 1. Should have wrote a c here, not a 1. So we have c to 3. And it's the c that's approaching 1 from the right. So we have the limit c approaches 1 from the right of 3 times 3 minus 1 to the 1/3 minus 3 times c minus 1 to the 1/3. So we have the limit as c approaches 1 from the right of 3 times the 3rd root of 2 minus 3 times c minus 1 to the 1/3. Now we can finally plug 1 in for c, and that gives us 3 times the 3rd root of 2 minus 3 times 1 minus 1 to the 1/3. Now the right side in this case is going to be 0, so we're left with 3 times the 3rd root of 2. Now that's only half of the answer. The other half comes from above. When we approached 1 from the left, that answer was 3. So if we add the 2 together, we get 3 plus 3 3rd root of 2. In example 7, we have an infinite discontinuity at an endpoint. It's 2 that is the problem here. So we have the limit as c approaches 2, and we're going from 1 to 2. So c will be approaching 2 from the left of the integral from 1 to c of dx over x minus 2. Well, that's equal to the limit as c approaches 2 from the left of the natural log of the absolute value of x minus 2. And we're evaluating that from 1 to c. So that's the limit as c approaches 2 from the left of the natural log of c minus 2 minus natural log of the absolute value of 1 minus 2, which is equal to the limit as c approaches 2 from the left of the natural log of the absolute value of c minus 2 minus the natural log of 1. 1 minus 2 is negative 1, but of course we're going to take the absolute value of that. So that's equal to the limit as c approaches 2 from the left of the natural log of the absolute value of c minus 2. Now if we plug 2 in, we have the limit. No, I don't want a bright limit. I want to plug 2 in. Now we have the natural log of 2 minus 2, which is the natural log of 0. And so we can't answer this one because we can't take the natural log of 0. This answer diverges. Test for convergence and divergence. When we cannot evaluate an improper integral directly, often the case is practice, we first try to determine whether it converges or diverges. If the integral diverges, that's the end of the story. If it converges, we can then use numerical methods to approximate its value. In such cases, the following theorem is used. And this is the theorem 6. It's a comparison test. Let f and g be continuous on a to infinity with f in between 0 and g for all x greater than or equal to a. Then, number 1 says, if we integrate from a to infinity of f of x dx converges if a to infinity of g of x dx converges. And on number 2, if we have the integral from a to infinity of g of x dx diverges if from a to infinity f of x diverges. So in example 8, we're going to investigate convergence. Does the integral from 1 to infinity e to the negative x squared dx converge? That's what we're trying to answer. In example 8, we're going to compare e to the negative x squared to something that we can actually take the antiderivative of, which is e to the negative x. Over on the graph to the right, I have e to the negative x squared in blue and e to the negative x in red. And where the two, well, let me put it this way, the two intersect at x equals 1, then after that, e to the negative x is below, e to the negative x squared is below e to the negative x after 1. So what we can say is 0 is less than the integral from 1 to infinity of, let's see, the blue is on the bottom, so we have e to the negative x squared dx is less than the integral from 1 to infinity of e to the negative x dx. Now because e to the negative x squared is positive all the time, it's really squeezed in between the 0 and the integral of the simpler version, which is e to the negative x. So if this thing converges, then this must converge because it's in between 0 and the value that we can find. So let's see if it converges or diverges. By taking the limit as b approaches infinity of the integral from 1 to b of e to the negative x dx. Now we can take the antiderivative of e to the negative x, which is negative e to the negative x, evaluated from 1 to b. That's the limit as b approaches infinity of negative e to the negative b plus e to the negative 1. Now, let's see how we can rewrite this a little bit. We have the limit as b approaches infinity of negative 1 over e to the b plus, we'll just leave that as e to the negative 1. And when we actually plug infinity in, we get negative 1 over e to the infinity plus e to the 1, negative 1, and negative 1 over e to infinity ends up being 0. So we have e to the negative 1, which is a value. So since the integral from 1 to infinity of e to the negative x converges, and our function we're looking at is in between 0 and that value, we say that it converges. In example number 32 in the book, we have the integral from 1 to infinity of 1 over x to the third plus 1. And it'd be very difficult to find the antiderivative of this function, so we're going to compare it to one that we can take the antiderivative of, which is 1 over x to the third. And off to the right, I've graphed both functions. 1 over x to the third is in red, and 1 over x to the third plus 1 is in blue. So as we can see, 0, we have 0 is less than the integral from 1 to infinity of dx over x to the third plus 1. is less than the integral from 1 to infinity of 1 over x to the third. So in this case, if 1 over x to the third converges, then our original function will converge as well. So we need to find the limit as b approaches infinity of the integral from 1 to b of 1 over x to the third dx. So we have the limit as b approaches infinity of, well, this is going to be x to the negative third. If we add 1 to that, that would be x. Add 1 to the exponent, that'd be x to the negative 2. And then we have negative 1/2. We're going to evaluate that from 1 to b. So we have the limit as b approaches infinity of 1 over 2b to the negative 2. Oh, not to the negative 2, and it's also negative. Negative 1 over 2b squared minus, and since it's minus negative, we'll just make that plus 1 over 2 times 1 squared, which is, then if we plug infinity in for the b, we get negative 1 over 2 times infinity squared plus 1/2. 1 over 2 times infinity squared is 0, so we have a value of 1/2. This limit converges, therefore the original function must converge as well.